So thanks to everybody, thanks especially to Daniel for putting up this very nice event, and to David and Soren for coming here and share their wisdom with us. Let me start by saying that I grew up as a co-integrator. Part of my thesis in Oxford was very highly influenced by David's view. I was lucky enough to arrive in a year where Clive Granger was visiting Oxford, and the year after Jim Stock had spent a sabbatical there, and David put together a group of his students working on these topics. As time went by, I wouldn't say I got disappointed, but a lot of issues, hesitations were in my mind. And today what I want to do, I don't want to be less complacent, I don't want to be rude at all. I just want to share with you and probably get help. This is like a psychological help to get rid of these worries that have been alarming me for a while. So there are fads and fashions in economics. This has always been the case in any science. So if you look at macro, it all started with ISLM, the Keynesian model, then that was rejected during the crisis of the 70s. You had real business cycle, supply, no demand. Then you had a little bit of demand coming back with the new Keynesian dynamic stochastic general equilibrium model. Then we had frictions in these models. We had DMP, we had Diamond, Mortensen, Pissarides. It started with frictions in the labor market, then in the goods market, then in the credit market. Nowadays, macro seems to be dominated by this work, Hank, which is not Hank Williams, a very famous country singer, but Hank means heterogeneous agents, new Keynesian models. So these are models of heterogeneity. We are no longer in a world of representative agent. As Jesus said, the mean will be the representative agent. Is not a thing of the past, but is of less importance than the quantiles, which is each of us, the individuals. That's Hank. When you look to micro, exactly the same. At the beginning, there were the foundations of consumer and firm theory. Then we put them together, general equilibrium model. Then there was the game theory, negotiation, bargaining, and so on. I/O, how firms organize, how different markets affect firms' decisions. Then there are auctions, how we sell things. Then there is learning, how individuals learn about their own behavior and policy rules, etc. Then there is sorting, how we get together, how firms attract workers, how workers choose firms, how men choose women or partners, etc., etc. And now we are looking, the latest thing in macro is networks. So basically how we make decisions in small groups and what's the diffusion process. If you look at econometrics, it's exactly the same. I think it started by the simultaneous equation models, Larry Klein, Price, the Cowles Foundation, etc. Then there was a bit of disappointment or disillusion with these procedures, 300 equations. I remember my first job was at the Bank of Spain. We had 300 equations in the model, and it was very hard to remember what was equation 61 or 32. And then, of course, there was a wave of disappointment from this procedure, and we moved to ARMA, which was basically one equation, univariate procedures, and so on. Then we moved to ARMAs in the variance, GARCH, and so on, with Rob Engel. Then we moved to VAR, small models. Then we moved to VARs with a bit of theory, which may or may not be credible, which is structural VARs. Then we moved to the world of panel because there was data was growing, not only in the time dimension, but also in the cross-sectional dimension. Then there was co-integration, looking at the long run. That's what we are focusing on today. Then there were non-parametric procedures. Then there was a search at looking for valid instruments, and really the plausibility of many of the instruments which had been used, especially in time series analysis, lags, etc., was a bit feeble. So we move into this new wave of diff in diff and regression discontinuity design, etc., where we're looking for very clean experiments. The economists have the obsession of being sort of second-order scientists. We are social scientists, we cannot replicate, and we wanted to be like the physicists of the, in the life sciences. Then we have factor models. It was already in the world of big data, so we wanted to reduce the dimensionality of these huge tons of data that we were surrounded, but our hard disk, our brain, has still limited capacity. Then we have quantile regressions, then we have had big data and shrinkage, and that's where we stay nowadays. So, of course, co-integration at its time, the 80s, the 90s, a little bit of the 2000s had huge hits. It had a huge influence on our profession. Here you have some co-integrating hits. We have the paper by Clive Engel and Rob Engel, 35,000 citations. This is probably number one. I think it's number one in modern citations accounts. Then the Soren's paper, surprisingly, his most cited paper is the one on Journal of Economic Dynamics and Control, more citations than in econometrics, than the econometrical one. And then just to cite a few, and forgive me if I'm included there, there is a textbook that I wrote with David, John Galbraith, and Anindya Banerjee. So, and I'm forgetting people like, I'm ignoring, not ignoring, but I'm not including people like Peter Phillips and many, many others who have made major contributions to this field. However, if you look at this is something that already appeared in one of the slides by Jesus. If you look at Google Trends, gives you some sort of information as the one that Jesus was giving you before. And it gives you time trends, but unfortunately, only to my knowledge, since January 2004, it gives you information about the daily counts of the words. So basically, this is co-integration and this is error correction. And what you see, of course, this is 2004. This is already when the topic was very mature, but the fad and fashion was years before. Somebody, I think Alvaro, mentioned that there had been 200,000 citations on the world, so you can make a backcast of how large was this. But if you look of the last 15 years, you see a declining trend, some sort of asymptote coming towards irrelevance, basically. So the question is, why has this happened? Why has co-integration sort of faded away? That's what I want to talk about. So basically, co-integration, I think wisely, came about as the converse, as the flip side to something which had been worrying econometricians for a while. They were aware since Jules' work, which is, and of course popularized later on by Granger and Nibble, which was the concept of spurious regression. So spurious regression, as its name indicates, as the label indicates, it's just the fact that you get a relation where there is none. So let's say, for those of you who are less familiar with these concepts, let's look at two variables, set t and xt, which are I1. Basically, what it means that for very large samples, the variance of this series is infinite. So it's infinite variability. And they have nothing to do with each other. David, in a very famous paper on alchemy of science, the econometrics alchemy of science, has this example of, David, accumulated rain in Scotland, and that was your, no. Well,
it was inflation in Britain, accumulated rainfall in Britain.
Okay, so it's inflation in Britain and accumulated rain. There may be some relationship because when it rains, maybe in England everybody still goes out with an umbrella, but people stay at home, so sales go down and prices may go down, etc. But basically what you find is a very, very strong relationship between these two variables. So but let's assume that they have nothing to do with each other. So now consider a regression of one of the variables on the other. So if you look at this regression, since the variables are totally independent, they may be even a little bit correlated, A is equal to 0, so set has the properties the error term in this regression, ut, has the properties of set. So if set has infinite variance as t goes to infinity, ut has infinite variance as t goes to infinity. So therefore, it it doesn't fulfill any of the properties of what we believe to be a nice error term for a regression. So that's not strange that is going to lead to all sort of funny results. So if we do the least square estimator of this regression, then what happens is, of course, that this coefficient that we estimate is different from 0. It's a random variable. It could be 0 with a given probability, but it could be 1,000 or minus 1,000 with another probability. And in some cases, this probability is not too different from a uniform. So it could take the same different values with very, very similar probabilities. So this is what it was a bit worrisome. The problem, of course, many of the diagnoses that we use in regression were not applicable to this case because, for instance, if we look at the significance of the coefficient, the slope is 0, so it should be highly insignificant. It just happened that as the sample size increases, the significance, the t ratio also diverges. The R square is a random variable. It's only the autocorrelation of the error term, which should be very high because the error term is a random walk, and therefore it should have an autocorrelogram that does not diverge. But the problem, as the cointegrating people notice, is that not that set t and xt are I1. That's not the problem. The problem is that there is not a single value of the slope of the parameter a such that the error term is stationary. There is no single value which makes that relationship stationary. However, it could be that if set t and xt share some common property, which is different from the divergence of its variance, that is, that they are cointegrated, there is a value of a such that set t minus xt is stationary. So we call that these two variables are cointegrated 1 minus a. In this case, the least square estimate of a is consistent, more than consistent, it's super consistent, but you have to change the formula for the standard errors because it's not the standard t or the standard normal distribution, but you can compute it. It can be derived from Dickey-Fuller's distribution and so on and so forth. So the problem is, so cointegration shed light on the opposite side, on the flip side, which was spurious regression. However, do we need all this cointegration toolkit, all this apparatus to avoid spurious regression? Well, if you add lags to the model, remember in the previous model we had set t on xt, then of course all these issues disappear because consider now the following regression model. I regress set t on xt and the lag of set t minus 1. Instead of putting xt, I put xt minus 1. This would look like an equation with predetermined variables belonging to a VAR. I regress one of the variables or lags of every variable in the VAR. Now, of course, remember set t is like a random walk. Xt is not in this regression. A is equal to 0 because they are independent. So in this regression, which is just adds this extra term, what is going to happen is that the OLS estimators is going to lead to b equal to 1, indicating that set is equal to set t minus 1 plus an error term, and a is equal to 0. So long as you have enough lags in a model, you are fine. Of course, you have to be careful with some inferences, including impulse response function, if there is a unit root, etc. But the solution, the recipe, is very natural and very simple. Forget about whether the variables are cointegrated or not for these purposes. Just add lags into the model, and all the problems of spurious regressions will disappear. So that's part of why there has been this sort of forgetfulness about the concept, because the way to deal with it, to tackle with it, was very simple. The other issue is about the cointegrating vector itself. 1 minus a, in my simple example, in the Johansen framework, you may have r cointegrating vectors among n variables, and therefore n minus r common factors. The problem is, of course, that A, which is the parameter, we have normalized this regression for set to have a coefficient of 1, is that we know A. So why should we care about estimating A? We know it. So if you think of variables, economic relations are typically multiplicative. So you have to take logs to get an additive, you have a linear model. So think of real wage and productivity. Think of a Cobb-Douglas. You take marginal productivity is proportional to average productivity. Wages is equal marginal productivity. So real wages and productivity are going to be co-integrated with a coefficient which is 1 minus 1. It can't, I mean, if you get something else, then maybe your production function is wrong, maybe your market is non-competitive and so on. But typically we need what is the coefficient. Consumption and disposable income. The log of disposable income minus the log of consumption is the saving rate. The saving rate is something between 0 and 1 or 0 and 100. So it cannot wander around like a random walk. It has limits, upper limit and lower limit. So if you get the co-integrating relationship, which is log of disposable income minus twice consumption, what is that? I know what is 1 minus 1, but I don't know what is anything else. It doesn't have any economic meaning, any economic concept. Real money balances and income. That's money velocity. So this is the log of money minus the log of price index minus the log of income, the log of GDP. So that's what it has, well, there is a concept. You may say, well, in a money demand equation, wealth should also be there, but we don't have data on wealth, and therefore income is correlated with wealth, so income is going to cut, the coefficient in income is going to catch whatever corresponds to income and whatever corresponds to wealth. But I mean, is not the optimal approach. The optimal approach is to get data on wealth, of which we already have quite a bit. Nominal exchange and price differential. So this is the purchasing power parity. It's the log of the nominal exchange rate minus the log of the relative prices. So if you don't get the coefficient 1 minus 1, what are you looking for? What does it mean that the log of the exchange rate is co-integrated with 3 times the log of the relative price? Long and short-term interest rate, the term structure. So again, the long-run structure, the long-run interest rate is a sum, it's a weighted average, maybe together with a risk premium with some specific properties. So if you take the logs, you are going to get 1 minus 1 minus 1, capital and output, consumption and income, consumption, income per capita and TFP, in the balanced growth model. Everything is 1 minus 1. Everything is 1 minus 1. Labor force and employment. The log of the labor force minus the log of employment is unemployment. Unemployment is between 0 and 1 or 0 and 100, like the saving rate. What would it mean if I get a log of labor force minus 1.2 employment? I wouldn't have the slightest idea. So this is why I think this concept has been losing ground, because more or less, whatever we want to estimate, we already know what it is. And if we are interested whether there is a long-run relationship, you just use a unit root test. You take this difference and test whether that's stationary or not. So for instance, here you have a very simple example. You have consumption and log of disposable income. The co-integrating vector is 1 minus 1. This is what theory would tell you, I mean, basic theory. There are more sophisticated theory, depending on the marginal rate of substitution, the properties, etc. You have here income, you have here consumption, the blue line, and if I just take the ratio, you see something. If you take an eyeball test of a stationary series as something which crosses quite frequently the mean, here you have a very stationary series. This is minus the saving rate. That's why it is negative. So what's the hell about all this co-integration stuff? It's just, I may test, I may use a Dickey-Fuller or a KPES or whatever to test whether that series is stationary or not. But why should I be wasting my time in using some maximum likelihood estimator, et cetera, to test something which is obviously this or nothing? The same happens, for instance, long run and short run interest rate. Here you have in red the bond yield, in blue you have the money market yield, so the short and a long run interest rate. This is the interest rate spread. Okay, the interest rate spread doesn't have a mean of 0. You can see that this series has some peak in here, which maybe it's an outlier, or maybe it's just a stream value of the distribution of the joint distribution of errors in there. If you estimate the residual from regressing, for instance, the short on the long run interest rate, you get basically because you put a constant, now it has a 0 mean, of course, by construction, but the co-integrating vector is exactly the one you should get from the basic term structure theory, 1 minus 1. Okay, and 1 minus 1 minus 1 minus 1, and you have different maturities in the interest rate. Of course, it is interesting that, for instance, if you do a VAR between the two, the impulse response from a shock in the long run to the short run is very sluggish, very persistent, because of course BT is an I1 process, right? When you look at the impulse response of the spread, that is the co-integrating vector to the same shock, of course what you see is a very non-sluggish process, a very temporary shock. Why? Because that variable, the co-integrating vector, is stationary. Therefore, any shock is going to die out at a given speed. Therefore, this is, there may be some, I'm exaggerating a little bit the message, there may be some cases where there are some doubt, some hesitation about the true values of the parameters, but in general, I think in most of the cases we address, they are known. So, of course, if you get something completely wrong, completely out of scope with the parameters that you have in mind, you are very Bayesian in these issues, you have to worry about either about the data or what has been happening and trying to find a reasonable explanation. So for the future, I would say that big data, I think, can resurrect co-integration, because it's a method, co-integration, remember, is a method of splitting the data into smaller parts, which could help us to think. On the one hand, we had the co-integrating relationships, which were these steady states towards the economy was converging, maybe linearly or non linearly, as Alvaro was explaining. And then the common factors, the factors which are behind the movement of all the variables. Okay, so I think in this sense, having big data, our minds are still small data. So we really need to reduce the dimensionality and explain a lot by a little. So I think the basic reasoning would still hold, and Jesus has talked a bit about that, but as long as we do not avoid doing black box econometrics, which I think that in some cases we have abused a little bit of that, it might not be such a successful. The resurrection may not be as successful as predicted. However, as I said, the flip side of co-integration is common factors. So you have plenty of data. It may be, rather than co-integrating, look at the other side. Jesus has a famous paper with Clive Granger where they basically compute the dual of the canonical correlations test of Sorin, and they identify the common factors in some interesting frameworks. I think co-integration can help, and it's already there's already a literature combining co-integration with the factor models, in the sense that the co-integrating, that the factors behind a factor model, people like Anindya Banerjee or Massimiliano Marcellino have been working on that, are basically the common factors, they're orthogonal to the co-integrating relationship. I cited just by chance the same paper as Jesus commented about, the paper by Onatsky about alternative asymptotics in large VARs. So now we are going to see some papers, hopefully important papers, with the words co-integration and large. That combination is going to be magic as part of the potential resurrection. So thanks for your attention, and the future is the next exit.